Okay, I've screwed this up twice. I just screwed it up in class, and then I made an adjustment to it and screwed it up again because just not being very attentive here. Okay, if you got the motion of two objects, I never did screw this up, but let's go start here. You got the motion of two objects, you got a lot of information, and if you read the question, it can be very confusing. Now, if you actually have the two objects in front of you, it might be easier to sort out. So one way to figure this out is to imagine a situation where you'd have these two objects. And the question that we're going to look at is going to have two balls rolling along inclines. That's fairly easy to imagine. And what you need to do is separate your attention. You need to first devote your attention to one object and ignore what you know about the other, and then the other object and ignore what you know about the first. Then maybe you have to put some things together. Some aspects of the motion of the first object will affect what you know about the second, and so forth. Your goal, default goal. Okay, there are often ways you can shortcut this default goal, and you'll see that when we do it here. Is to find the equation of motion for the first, call that x1 of t. Find the equation of motion for the second, that's x2 of t. Now there might be something about x1 of t that you need in order to find x2 of t. That will be the case in the example that we're going to do. Now, alternatively, if it's a uniform acceleration situation, which this problem, the problem we're going to illustrate is, you can go to motion on an interval analyzed by thinking about trapezoidal graphs, using the equations of uniformly accelerated motion, by direct reasoning, by various more intuitive methods, okay? And I always encourage that you do things intuitively, but you also have to be able to do them symbolically in terms of the functions and so forth. Naturally, if you know x1 of t and x2 of t, if those functions are differentiable, you can find the velocity and acceleration functions. Often you'll know at least one of the acceleration functions or be able to get it relatively easily. And then you can integrate those, assuming you have some initial conditions or boundary conditions on x and v and or v. Okay, well, you don't need to understand all that last mumbled paragraph, but if you do, great. So, I started doing this symbolically and realized when I got about here I was going to have to give you a numerical example, and I said, nah, you're not going to understand it as easily. Better to do the numerical example and then follow up with the symbolic. And I had the symbolic written out, it just didn't get emailed, so I didn't have it when I got here, so I wasn't able to share it. And I will get that so you can relate it to this example. Okay, now I've screwed this example up twice just by doing bonehead things. And not checking myself. So I'm going to show you how you want to check yourself and how I should have checked myself so I wouldn't have made those mistakes. If your first object goes 200 centimeters from rest in 6 seconds, well, that's one part of the problem. The other part is the second object starts when the first object is 20 centimeters down its incline and catches up with the first object just as they reach the end. Well, let's not worry about the second object. Knowing that the first object goes 200 centimeters from rest in 6 seconds, we say, okay, I don't care what else there is in the problem, I can figure out the acceleration of that object, I can figure out its final velocity, I can figure out its equation of motion. Okay, so all that's in the ellipsis here. We just say, okay, if it does this, we know that the acceleration is 43rd centimeters per second, 43rd centimeters per second squared. So your x1 of t is half at squared as 23rd centimeter per second squared times t squared. How did we get that? Very easy. 240 centimeters divided by 6 seconds is 40 centimeters per second. That's your average velocity. Initial velocity is 0 because that starts from rest, so the final velocity would have to be 80 centimeters per second in order for the average velocity to be the average of the initial and final velocities. The assumption that's kind of implicit here, I didn't state it, is that acceleration is considered to be uniform. Okay, now does that really work? Okay, well, x1 of 0 is going to be 0, That was an implicit assumption. We assume x of 0 is 0. Assume that this thing starts at t equals 0 at position 0. Okay, so x of 0 will give you 0, and x of 6 seconds, square 6 seconds, you get 36 seconds squared. Divide that by 3, you get 12 seconds squared. 12 seconds squared, yeah. And you multiply that by 20 centimeters per second squared, and you get 20 times 12, which is 240 centimeters per second squared times second squared is centimeters. You get 240 centimeters. So, as I should have done in the first place, I checked this, and now it seems to check out. So we're pretty secure. Now that's just using one little bit of information given in the problem, okay? Now we use what we know about the second object, that it's released when the first is some distance down the incline, and in this case we'll assume distance 20 centimeters. Okay? So that occurs when? Well, when x1 of t equals 20 centimeters. Now, there was an error here that's pretty instructive error. This is a basic thing you have to understand. Why not just say, okay, the average velocity is 40 centimeters per second. So in order to go 20 centimeters at 40 centimeters per second, it only takes half a second, so it must be there in half a second. What's wrong with that? People had a little trouble telling me what was wrong with it. They kind of thought that wasn't quite right. Well, that's an example of formula grabbing. You take an initial velocity, or you take an average velocity and you divide it into some displacement, and you get a time, and you think it applies. The problem is that the 40 centimeter per second average velocity is for the motion from here to here. Okay, it's not for the motion from here to here. From here to here takes less time, and you get less speed. You build less speed. The average velocity here is clearly less than here. So you can't apply the average velocity here to this interval. But you will, unless you understand what you are doing, and maybe draw some trapezoids and some graphs and check yourself out, like I didn't here, you know. Just take a lesson from my error. Okay, anyhow, how do you find how long it takes? Well, there's your position function. You set that equal to 20 centimeters and solve for t. Okay, well, that's very easy. It's convenient you have a 20 here and a 20 here. You get t squared equals 3 seconds squared, so that t is plus or minus the square root of 3 seconds. And we, you know, the negative square root of 3 seconds is not in our domain. The domain of this x of t function, and it doesn't hurt to write this out, the domain is t is greater than or equal to 0. And since negative square root of 3 seconds is not in the domain of this function, it doesn't start moving until t is 0. You don't know what it was doing before t equals 0, but it probably wasn't following this. Okay? Now, it actually is possible it was. Maybe it was rolling up the incline before t equals 0 and came to rest for an instant at t equals 0 and came back down, in which case the negative square root of 3 seconds would be relevant. And you kind of want to think about that. Maybe make yourself a note, because that does arise very soon in some of the problems that I think are assigned. Okay, well, then square root of 3 seconds, that's 1.7 seconds. Now, if we're doing the experiment and just using our own rhythmic count to determine accelerations and so forth in centimeters per count squared and velocities in centimeters per count, our count's not going to be accurate enough to want a more accurate version of square root of 3. Okay, your calculator will give you square root of 3 out to 10 digits or whatever, more than that if you ask. That's you wouldn't use those. You wouldn't write out all the digits. You would write out the number of digits that's appropriate to what you're measuring. Okay? And if you're measuring with your own rhythmic count, you're not going to be accurate to another decimal place. So there's no point in using another. If you're doing it with an accurate timing device, and if you're using the microphone and the vernier interface carefully, you get much more accurate information, and if you're measuring everything else carefully, then it might be conceivable you could do it to 1.73. 3 significant figures, which would kind of be plus or minus 0.5%. And it doesn't hurt to go to a 4th significant figure, but you wouldn't want to go beyond that because you can't measure things any more accurately than that. So, you know, that digit there would be questionable, but that digit might not be quite enough. So you make judgments based on the accuracy of your data. In any case, back to the problem, we figured out the motion of the first object, the equation of motion. We've used that to figure out how long it takes to get to the 20 centimeter position, and that's when the second object is going to be released. So we've been able to find x1 of t. We had to use x1 of t to get information that we need in order to do x2 of t. Or alternatively, as we're going to do, we're just going to look at the motion on an interval, because that's going to be very easy to analyze. Okay? So our delta t2, the time that it takes the second object to get all the way down the incline, is going to be what? Well, they get together when t equals 6 seconds. This one starts at t equals 1.7 seconds, which is what I'm going to use here. So we get 4.3 seconds for the second object to go all the way down the incline and just catch up with the first, to be at the same position as the first after 6 seconds. Now we easily analyze that motion, and we find that its acceleration is 12.6 centimeters per second squared. Its velocity is going to be what? Now let me see if I did that right. Okay, I got that, and actually I don't think that's going to be right, so let's modify it. Okay, 4.3 seconds. If it was 4 seconds, then it would average 240 divided by 4 is 60. It would average 60 centimeters per second squared. Okay, well, 4.3 is what? It's about, it's 7.5% more than 4. So the average velocity will be 7.5% less than what I just said. 7.5% of 60 is 4.5. So it's closer to 55 centimeters per second, 55.5, if I'm doing that right. And there's an approximation in that because the reciprocal doesn't go with the exact percent, but for small percents it does. So you might want to think about what I mean, but I don't expect you to know it now. So I think it averages about 55, 112, 111 centimeter per second final velocity. And we probably want to call that V2F to distinguish it from the final velocity of this one, which is what? Well, average velocity 40 centimeters per second. Final velocity is going to be 80 centimeters per second. Okay, well, part of the question was, what's the relative velocity? How much faster is this going? Well, it looks like it's going about 30 centimeters per second faster. That would be the relative velocity of the two balls. Okay, now my acceleration isn't right. I've got to divide this 112 by the 4.3. Okay, and it's a little bit like dividing 120 by 4. It's going to come out closer to 30. I'm having trouble getting 30 from the 12.6 that I did there. But I'm going to say it's going to be roughly 30 centimeters per second squared. You divide the final velocity by the time. Okay, so there's that much analysis. Do you see how that analysis fits into this scheme, which is my main point here?